Welcome, dynamic students. This mini lecture will concern itself with looking at velocity and acceleration of two different rigid bodies moving in planar motion. So up till now, we've only talked about the relating acceleration and velocity of two different points on the same rigid body, and maybe comparing that to some fixed inertial reference frame. Now we're looking at two distinctly different rigid bodies, both of which are moving at the same time relative to an inertial reference frame. So we've got this problem being drawn from Hibbler's 14th edition dynamics textbook, section 16.8, and this is problem 16-138. So for this we have a kind of a hinge that is bolted to the ceiling, shown here with a little dashed. And so this hinge here, and we can call it point A, this is going to represent what I'm going to call our fixed reference frame. It's fixed, it's bolted into the ceiling. If we were going to start applying Newton's laws and looking at the kinetics of the problem, we would call this our inertial reference frame. We've got suspended from that hinge, we've got a solid hoop. This is all one rigid hoop with an average inner diameter, we can call it an average total diameter of 0.2 meters. And that hoop is itself rotating, kind of swaying in one direction. It's rotating about point A with a given angular velocity and acceleration. At the same time that the hoop itself is rotating about point A, we'll call it the center of the hoop is at O, we've got a little collar that's hollow. So this is like a little tube, and it's sliding along the tube. It's moving at this point to the left, and it's got a velocity relative to the hoop. We don't know what the velocity is relative up here to the fixed point, which is what we're going to find out. But it's got a velocity relative to the hoop at this instant in time of 5 meters per second to the left, and it is increasing its speed at 1.5 meters per second squared relative to the hoop. So we've got two bodies, they're both moving, and we know the relative motion of one body to the other. We know the motion of one body to a fixed reference frame, and now what we want to know is the motion of the first body to the fixed frame. So we can invoke our expression that was derived in this section of Hibbler, and also in my notes if you're using them for this class, of relating the acceleration of a point on one rigid body that's moving to the acceleration of another rigid body relative to a fixed reference frame, and the angular acceleration and angular velocity of that first body relative to the fixed reference frame, and then get your acceleration of the first body versus a fixed reference frame. You followed all of that. We're just going to write that out with math because it's a lot easier to say. We're going to call the collar body B, and we're going to call the hoop body H, and we're going to call point A up here the fixed frame. So I'm going to refer to the motion of this collar as the motion of body B, the motion of the hoop rotating around, the motion of H, and then the bracket up here that's bolted to the ceiling is F. So what I want to know is the acceleration of B relative to F. That's what I don't know. I can say, given what I know about relative accelerations of two bodies, I can say that's equal to the acceleration of B relative to H, something I do know down here, plus the acceleration of H at the point where B happens to be located on H relative to the fixed frame. So this isn't just the acceleration of h anywhere on h. It's the acceleration of h at a particular point on h. That's the point where b happens to be. So this is the only real tricky part of the expression that we're going to have to find. Plus 2 times the angular velocity of h, which of course, given that we're in rigid body planar motion, it's going to be in the k-hat direction, crossed into the velocity of b with respect to h. So you're going to hear with respect to a lot when we're talking about these multiple rigid bodies moving. So this is all about with respect to what? So this is what we want to find. We should know something about this. We were given some information. This is something we should be able to find, but we're going to have to be careful to find it at the right point. This we were given, and again, this is something we were given. Okay, so let's just break these out, and I'm gonna use different colors just to make it a little more clear. So what is the acceleration of body B with respect to body H? So for that, we pretend the hoop is standing still. We just kind of fix it. We forget that it's moving relative to anything else, and we just stand on the hoop reference frame, and we see that the bead is this little collar B is just moving this way. So we can use, hey, it's moving in a circle. So we can use our curvilinear kinematics to write that expression. So we can write an expression. Oh boy, let me get a. I'm gonna use an I hat j hat coordinate system, which I'm going to attach to my fixed reference frame out here. But I'm going to use that convention for everything, which means theta is going to be positive in that direction. Okay. So basically, these are both negative. But my tangential velocity and acceleration here are, oops, they're both negative. Okay, so go back to blue. Always forgetting this coordinate system. It is so essential to write out your unit vectors and your default positive and negative directions. You will end up with a sign error nightmare if you don't. And remember, a lot of times if you have, say, a slope or some other curvy system, you won't always want your ij unit vectors going in the same direction. You might be writing tangent normal if you're following a curve. So it's really essential that you write that and then reference it. Wait a minute, is this positive? Is this negative? Because you're writing velocity, and in some cases you're writing radius vectors. So am I going in the positive or negative direction? Which direction am I twisting? So that was really important to write. So you're going to see those sign conventions followed. Okay, tangential velocity in this case, or tangential acceleration, it's in the negative I hat direction. So we have negative 1.5 meters per second squared I hat. And then, of course, because we're traveling in a curved path around that hoop, remember, the hoop's not moving from our point of view with reference to the hoop. So we've kind of fixed the hoop. We're only looking what's going on the hoop. Remember, we have our sort of our centripetal, our normal acceleration, which is the velocity of b all squared divided by the radius of curvature, which is, of course, just our 0.2 meters. So this should look real familiar. This is just curvilinear motion. So we can write this equals negative 1.5 meters per second squared I hat plus, we're going to end up with something pretty big, 125 meters per second squared j hat. Okay, so that's this term. Okay, next, I'm going to try switching colors here. Next, we're going to look for the acceleration of the hoop at the point where the collar happens to be sitting relative to the fixed reference frame, which is the ceiling, basically. Okay, wow. Okay, the hoop's rotating about a fixed point. That makes it a little bit easier. So the acceleration of point A is 0, and we want to know the acceleration of a point down here. This is the point we care about. I'll put a little star here. So if we look at a radius from point A down to this point where the collar happens to be sitting, the point on the hoop at B, we can think of this as just a point on the larger fixed circular motion that is this point at this instant about A. So it isn't just any point on the hoop, it's the point where B happens to be. Okay, this is fixed pivot. So from the point of view of the hoop versus the ceiling, the hoop's just rotating about A, and we know how it's rotating. So we can just use relative acceleration of 2 points on one rigid body. So we're going to look at our particular point of interest at B with respect to our fixed reference frame is going to be equal to the acceleration of the hoop at point A relative to the fixed reference frame plus alpha hoop, we'll call it H, which we know is in the k-hat direction, cross R from A, the point we know, to B, the point we care about, minus angular velocity of the hoop squared R from A to B. Okay, we were given this, and that is going to be a negative number. So we've got, because we've defined positive as counterclockwise, so these are going in the clockwise direction. So that's going to be negative 3 radians. Oops. Which one's the velocity and which one's the acceleration? We need to fix our units up here. Boop. So this is negative 3 radians per second squared. And the radius vector from A to B is going to be in the negative j hat, and we use this larger radius because that's basically the radius from the 2 points we care about now. So this is going to be negative 0.45 meters j hat. And then again, our omega here is our 6 radians per second. So if we basically multiply all of that out, we end up getting an expression, which I'll continue that over here. Acceleration of the hoop at point B with respect to our fixed reference frame is going to equal something that's reasonably simple. Make sure I get the whole thing here. We should end up with a negative 1.35 meters per second squared I hat plus 16.2 meters per second squared j hat. And so that was just evaluating the cross product, multiplying this by our negative 4.5 meters j hat, and collecting terms. So we have a little bit simpler expression. So we've got one acceleration expression with components in both vector directions, and now we've got another. Okay, so we've got that one and we've got that one. Now we just have this expression to evaluate. That's the last one. So we'll go to yet another color to look at that one. So that's just 2. And the angular velocity of the hoop, and it's negative, but we're given the magnitude, so we've got negative 6 radians per second. And we're going to end up crossing that. That's in the k-hat direction. We're going to cross that into our velocity of B within the hoop reference frame, which is negative I hat. So that's going to be negative 5 meters per second K hat cross I hat. Ooh, cross I hat, not cross J hat. Cross I hat, which is, of course, J hat. So that's going to give us 60 meters per second squared J hat. So we're going to add them all up. We're going to have basically this one, and this all added together to give us that. So I can go back and tally them up. Say acceleration of B, my little collar, with respect to the fixed reference frame, the ceiling, is going to equal negative 2.85. I'm collecting terms in each vector direction. I hat plus 201.2 meters per second squared J hat. So the magnitude of this, which might have been what the question asked for, it didn't. This is the whole vector expression, so I can apply the Pythagorean theorem, which is going to give us something that's pretty close to just 202 meters per second squared. The question also asked for velocity, which honestly is much easier. Kind of a bit simple compared to the acceleration, but we can go ahead and work it out anyway. I'll go back to blue for that. The velocity of our collar B with respect to the fixed reference frame is just the velocity of B with respect to the hoop plus the velocity of the hoop at point B with respect to the fixed reference frame. So we know that this is just negative 5 meters per second I hat. We've already used that up here in our other derivations, and when we look at the velocity of the hoop at point B with respect to point A, we can just use this and this radius effectively and say we've got negative 6 radians per second K hat crossed into our radius. So we're basically just doing, we're applying what is the motion of point B with respect to point A, just looking at the hoop's motion only. We're pretending the collar isn't even there. We're just looking at the point where the collar happens to be on the hoop, and that's what this notation means. So we've got negative 0.45 meters J hat, because we went from point A to point B. So that gives us 2.7 meters per second negative I hat. Add that to this, and we get the velocity of point B with respect to the ceiling due to its motion relative to the hoop and the hoop's motion relative to the ceiling is 7.7 meters per second in the negative I hat direction. We'll call it kind of left. So that is the end of this mini lecture. We've used kind of a simple example of a fixed pivot describing the motion of one rigid body and a known circular motion of another rigid body, and our known already derived relationships for acceleration of one body relative to fixed reference frame given a knowledge of the acceleration of another body and the relative acceleration of the two bodies. Key in all of this is this concept that we discussed of A, H, B, and V, H, B, F. You'll see this notation in my notes and possibly other sources. The lower number is the reference frame with which we are looking at motion. The first letter is the body we're concerned with, and its subscript is the point where the motion is being examined. So that's the key, knowing that we're not, when we look at the acceleration of the hoop with respect to the frame, it's at the point of B, because the acceleration of that hoop is different everywhere depending on where you are on the hoop. And that's the key to this problem, and a lot of the others like it, is finding that point of interest on one body which is usually where the other body happens to be located, that contact point where they're together, or where we're assuming they're coincident. So that's it for this lecture, and have fun practicing these problems on your own as you work through these concepts.